Okay, so let's start. Okay, so this is where we are. Kind of a summary of what we've done in the last couple of weeks. We talked about Bayesian learning. We are talking about Bayesian learning. Talked about what does it mean for us to be Bayesian, and talked about the fact that actually we have a flexibility of deciding what do we want to be Bayesian about, whether it's the set of parameters, whether it is the class of functions, and these are different. We talked about one specific important example of the naive Bayes algorithm, and gave a few examples. Hopefully this is, and also try to explain, what are the assumptions and why does it work even when the assumptions do not necessarily hold. And last time we talked about EM, basically a general paradigm to learn in the context of latent variables, hidden variables. And then we actually closed last time by showing, again, another link to discriminative learning, right? So we gave a story, and this is something that I really want you to understand, where if I was to give you the story a month ago, you would immediately know this is a supervised learning scenario. Given that I'm giving it to you last week, we also have another option of thinking about it from the generative model perspective. So now we have two ways of thinking about modeling the same data, right? So the data was basically n plus 1 tuples, right? So vectors of size n plus 1, I'm giving it to you. And I told you also that at the end, I'm going to take one of these, yn or y0, or xn or x0, I don't remember which one it was, and I'm going to ask you to predict it given the other n. So it's a standard supervised learning scenario. We also modeled it as learning, as a generative model with latent variable. And the question is, which is better? So it's a situation where you now can think about it using everything you've learned in this class. So that was EM. And you're going to get a chance to basically write it. And we wrote down update rules for two cases. You're going to get a chance to write down update rules for one other case in the problem set. Questions about where we are? Okay. So today I want to move beyond that. Still, we are in playing the same game of probabilistic learning. I want to talk about representing arbitrary probability distribution, and then we're going to move to talk a little bit about inference. We'll see what that means, and learning of these representations in the next couple of lectures. Okay, so this is the game we're playing now. We're thinking now about unsupervised learning. Given data, think about it as just like what I did at the end of last time, n plus 1 tuples. I don't have a notion of a class label, at least not a prior notion of a class label. What we want to do is after we see data like that, n plus 1 tuple, we want to be able to say something about the data. I know something about correlations between variables. Perhaps we want to be able to compute the probability of some events. An event here, by event here, we mean a subset of the space. The interesting thing is going to be that you want to compute the probability of event that you haven't observed, right? Otherwise, would be less interesting, although even that would be interesting. So we want, in our terminology today, what we want is to learn the most likely model that generated the data. Once we have this model, we can answer a lot of questions about this model, make predictions, compute probabilities, and so on. So here is one example that we've seen, just looking at it slightly differently, right? So we already looked at one family of representation for probability distributions. And this is the example that we looked at, right? This is the naive Bayes example. So we had one variable y. Given y, we had n other variables. And we said that in order to do something with this model, specifically what we wanted to do here is we thought about it as a prediction problem for this variable y, given the observation, which was this example, n features. And we said that we're going to make, in order to make this model tractable, we're going to make this independence assumption. So the assumption was that xi was independent of xj given y, conditional independence of the features. Under this assumption, we knew how to write the prediction for y. So the question we're going to ask today is, can we relax these assumptions, deal with more general probability distributions, and what can we do with it? Can we learn this? Can we make decisions with respect to this? Okay, so let's just go back to this simple probability distribution. So under this assumption, we can actually compute the joint probability distribution. That is, we can compute P of y, x1, x2, xn. And again, what I mean by that is, this is a notational convention that you should be comfortable with. Excuse me? Excuse me. Too much noise. Bothers your neighbors, not only me. Thanks. So we want to be able to, so the notation here is P of y equals something. So let's assume that all of these are Boolean variables. Really, this stands for what's the probability of P of y being 0, x1 being 1, x2 being 0, xn being 1, or something like that, right? And we've written this way. We said that we can write this as P of y times the product P of xi given y. Everyone is comfortable with deriving this? Okay. So now that we have a joint probability distribution, you can do whatever you want. Any event that I ask you, before we focused only on, okay, given the xi's, give me the y. But I don't need to do this, right? I can just invent any event. Let's say the event x1 equals 0, x2 equals 0, y equals 1. And I can compute it also because I know the joint. So the generic way to compute it is to marginalize over all those variables that are not specified. That is, you write down here P of y, x1, x2, x3, up to xn. You fix y equals 1, x1 equals 0, x2 equals 0. These are the assignments that you want. And all the rest will be something. And you sum over all the somethings that the rest can be. Okay? This should be clear that this probability is the sum over how many assignments do I have here? Almost 2 to the power of n minus 2. It's a little bit more than n minus 2, right? So I have a lot of, this sum is a big sum, but it computes this, the probability of this event, right? That's clear. Now, because it's such a big sum, if n is any reasonable number, you don't want to do it this way. And there is a much more efficient way of doing it, right? So again, using so this is a generic statement, right? Every time when you have n plus 1 variables and you want to compute this, you can do it this way, by summing over 2 to the n minus 2 assignments. In this specific case, because of our independence assumption, we can say, well, I don't need to do it this way. I know that the probability of this event can be computed as P of x1 being 0 given y, P of x2 given y, P of y. Everyone agrees with that? Again, just write this down, use product rule, and the independence assumption, which is written here, and you will get it. So this should be kind of a 2-line proof. again, you can also read it directly from the graphical model. This graphical model is a convention, which I'm going to generalize in a second, that basically says, because I have a variable here and arrows down to the children, I'm assuming that the children are independent given the parent, and therefore I only care about these numbers. Okay? So we can do whatever we want, right, with respect to this simple representation of distribution. And again, the question is, can we do better? Can we do better with respect to more complex probability distribution? So we want to move to other probability distribution. And the first thing I want to mention is that a probability distribution is just a function. It's nothing mysterious about it. It's a function that satisfies a few properties, very small number of properties, maps, in our case, say, the Boolean cube, x1 to xn, to the range 0 to 1, and that's it. So there are many, it's not surprising that there are many, many ways to represent a probability distribution. The most simple one would be just to write a table, right? So let's assume you have a probability distribution over the Boolean cube, let's say of dimensionality 5. So there are 32 different entries. And you can write 32 different numbers that sum to 1, and you have a probability distribution over it, right? That's the only thing. We just need it to sum to 1. Only that for large n, this is not a feasible representation, right? You need 2 to the n minus 1 numbers. 2 to the n minus 1 because they have to sum to 1. So the last one is a function of the 2 to the n minus 1 that I've written. But I can do other things, right? So there are many other representations. But if I want to come up with a representation that does not require me to write 2 to the n minus 1 numbers, we'll have to make an assumption, or many assumptions, right? Because the general probability distribution is going to require 2 to the n minus 1 numbers. So we're going to make assumptions. But given these assumptions, we can do a lot of stuff. So I'm mentioning here, first, multilinear polynomial or multivariate polynomial, if you want to think about it. This is just a functional representation. Multivariate polynomial is the generalization, if you want, of a DNF. Right? So you have x1 times x3 times x7 plus x2 times x5 times x7 plus, and each one of these products or monomials can have a coefficients. And if you normalize this, this is the probability distribution. The nice thing about this probability distribution that is actually becoming a relatively hot area now about this representation is that actually inference with these representations is efficient, a lot more efficient than on all the standard representations. But we're not going to talk about this. So we're going to talk about two others, or in fact one of these, Bayesian networks, graphical representation of distribution, which are also very popular. There are good reasons to like graphical representation of distributions, either whether they are directed, Bayes nets, or undirected, Markov nets. And the reason is that it's easier, let's say, to understand the probability distribution. It's easier to understand what are the dependencies or independence assumptions that are being made. Whether this is the best representation to use, it's still not completely clear. People like it. But in many respects, at least the argument that I and others have made when we thought about this representation was that Bayes nets were very good in the time where you actually wrote down your representation manually. You had a small enough number of variables that you can write down a representation, and you looked at the representation because you could understand it. But once we have huge amounts of data, and we deal with very large representation of distribution over large dimensionality, many variables, we typically don't write down representation of distributions. We learn representation of distribution. And therefore, the comprehensibility argument is no longer that valid. So my expectation is that more and more people will move to deal with these kind of representations. But we'll see what happens. So today we're going to talk about Bayes nets, which is really a very nice representation that we can understand and has a lot of nice advantages. So as I said, we already dealt with one Bayes net. This is a Bayes net, a very simple one. And we argued, at least, hopefully you're convinced that we can compute the probability of any event with respect to this. And we want to relax these assumptions. So here is how we relax these assumptions. We move to a general directed acyclic graph. And here is the example. So here we're going to make another independence assumption that will be clear in a second. So let's, first of all, I have nodes here. I have edges, directed edges. And it's a graph. It's a directed graph, and it's acyclic. So there are no cycles, directed cycle, no directed cycles. So just a definition. So if there is an edge from Z to X, I'm going to say that Z is a parent of X. If there is a path that leads from Y to X, I'm going to say Y to X. I'm going to say that X is a descendant of Y. So it could be a child or grandchild or more. There is a directed path. So with this definition, the independence assumption that is encoded, this is the convention that is encoded in this graph, is that X, a node X, is independent of its non-descendants given its parents. Okay, so Z here is independent of all those that are not descendants. The descendants are X and X2 in this case. So given Y, it's independent of all these. This is not the only way to write the independence assumption. There are other ways, and I'm going to give you one other way later. But to me, this is the most convenient way to think about it. Why is it the most convenient way? Because with this convention, you can always write the joint probability distribution, P of Y, with all the variables, where in this case I have just Y, single Y here, as P of Y times the product of the probability of each variable given its parents. Okay? So this is actually something that you should prove to yourself. You can see that it's very, very similar to what we had here. Also here we wrote it as P of Y times P of Xi given the parents. The parent was just a single parent Y. So this is a simple generalization. But really it's a theorem, right? It's a theorem that I can write it this way. You can prove this theorem very easily. In order to do it, you should choose an order of the variables and then take the joint and decompose it step by step using the order that you choose. My suggestion is start with the leaves. In this case, start with X10. And then you can write the joint as P of X10 given everything else times P of everything else. And then P of X10 given everything else, given the independence assumption. X10 has no descendants, so it's independent of everything else given its parents. So you're going to get P of X10 given the parents. And you continue this way. Again, start with the leaves. So decide on an order that starts with the leaves and goes up. If you start with a different order, you may get a more complex product here. But so the order matters here. It doesn't matter to the answer. It just matters to how simple the answer, you write the answer. Yeah. No, they are not. The only independence assumption I'm making is this, that a variable X is independent of its non-descendants given its parents. X1, this is one example. This is a generic statement that says every variable x here, whether it's called z or x2 or z3, for all variables, this is the assumption that I'm making, that a variable is independent of its non-descendants given the parents. That's it. Yeah, and we're going to do it in a second. We're going to see that this is enough information for us. Well, we have to add a little bit of information. But given this assumption, we can we can do inference. By inference, I mean we can compute the probability of any event that you like. In particular, I can compute the probability of z being 1, z3 being 0, and y being 1. Okay, so we'll get to it. But basically, this is the assumption. And the important thing that you have to remember is that writing it this way really requires only the product rule, but it depends on how you choose the order of the variables. Now, notice that what I have here is I have this general expression of P of variable given its parents. This general expression is called a conditional probability table, CPTs. And once I have these CPTs, this completely determines the joint probability distribution. So what are the CPTs that I need here? Okay, let's start with this example, and then we'll get to the. So just to understand what we are talking about. So the nodes here are random variables. Edges, you can think about it as representing causal influences. Doesn't necessarily have to mean causality in any way. And each node here is associated with conditional probability tables. So, for example, Z3, from this expression, you know that all I care about is the probability of Z3 given Y. But for X, you care about the probability of X given Z1, Z2, Z, and Z3, because these are the parents. So in some cases, the conditional probability tables are simple. Here, it's going to be, say, two numbers, P of Z3 being 1 given Y being 0 and Y being 1, and P of Z3 being 0 given Y being 0 and Y being 1. But for X, it's going to be a lot more numbers, right? Because it's going to be P of X being 1 given any combination of the parents, 16 combinations. Agreed? So 60 numbers, and then P of X being 0 given these 60 numbers. 32 numbers. Of course, you really need to represent 16 numbers because the others are just 1 minus them, right? Correspondingly. But it's going to be much larger. So this is what we have here. You can think about this as just a data structure that represents a joint probability distribution. Instead of the table that I suggested at the beginning, that is also a data structure of size n to 2 to the n, here I have a more compact data structure. It's more compact because it really represents a set of conditional independence assumptions about the distribution. Not everything is representable. Well, in fact, it's a universal representation in the sense that any probability distribution can be represented this way. But once you fixed one, it does not represent all probability distribution. Okay, so let's take an example. Here is a short story, and we want to be able to model it, right? So we have a burglar alarm. It rings when there's a burglary or an earthquake. An earthquake will be reported on the radio. And if an alarm rings, your neighbors hear it, they will call you. So I want to model it as a probability distribution, as a base net. The reason I want to model it is because I want eventually to answer questions. For example, what would be a question that you could ask here? Is there a burglary happening? Yeah? Right, so I got a call from one of the neighbors. Is there a burglary? Yeah? So what's the probability that your neighbor calls you given that there is an earthquake? Yeah. So I can ask a lot of questions. So this is, you can see the power of this modeling here, right? I don't need to decide ahead of time what is my variable of interest. I model all the situation, and then I can ask many questions. Yeah. So hidden Markov model is another representation of a probability distribution, just like BaseNet. It also makes independent assumptions. And in this specific case, it seems like hidden Markov model will not be a good, the type of assumptions made there will not be a good fit for this. But it's just one example of a BaseNet, in fact, because it's a directed graphical model. It's a very simple BaseNet because it's also a tree. So we're going to get to it. OK, so first of all, we have to model it. I mean, you kind of modeled it already because you chose variables to query. These are the variables that we'll choose, right? So we'll choose we'll think about all of them as Boolean variable. Was there an earthquake, yes or no? Was there a burglary, yes or no? Did we hear the alarm, yes or no, and so on. So I have these are two neighbors. And then I want to be able to model the information that we have. For example, if there's an earthquake, you'll probably hear about it on the radio. So I want to model it. An alarm can ring because of a burglary or an earthquake. So I'm going to model it by making these independence assumptions. Notice that once I drew the edges, I determined all the independence assumptions that I've made. And these make sense. Now, we can think about several things. First of all, how many parameters do we need? So let's think about how many parameters do I need in order to model it. So we have to go over all the conditional probability tables and see how many parameters. Remember that if I have 1, 2, 3, 4, 5, 6 variables, modeling it as a table requires 2 to the 6 variables, right? 2 to the 6 numbers. Let's see how many do I need here. So here I have, in order to model earthquake, I need 1 or 2. Let's call it 2. Let's assume that we don't do the 1 minus now. So two numbers, P of earthquake being 0 or 1. 2 here. Someone needs to add the numbers. OK, so these are the cases of 2. How many here? 4, right? So P of radio given earthquake, where each one of them takes 2 values. 0 given 0, 0 given 1, 1 given 0, 1 given 1. Same thing here, 4. Same thing here. How many here? 8. So I need to have P of 1 given each one of the 4 combinations, and P of 0 given each one of the 4 combinations. OK? So altogether, I think we got 4, 4, 4, 12, 16, and 8, 24. We saved a little bit. And in fact, we need half of this because I counted everything. So, OK, so that's it. Now, the good thing is that now I can compute the joint probability distribution. And again, given the independence assumption that this graph conveys, as a function of all these conditional probability tables, CPTs, I can now write this. So how will I write it? I'll look at the graph and I'll say, OK, so the joint is P of E given everything times P of everything. And then I'm going to say, oh, in fact, of P of E given everything, I can just write P of E because it's independent of everything, given that I know this. And then I have to refactor this. And again, I'm going to choose an order, P of B, given everything, times P of everything, and so on. At the end, hopefully I convinced you earlier, and you'll have to do this exercise yourself to convince yourself. I'm going to get P of E, P of B, P of R given E, because of this, P of A given its parents, alarm given the parents, P of M given the parents, and P of J given the parent. So once I give you the conditional probabilities, then the numbers in the boxes here, you can compute the joint probability distribution. And this is easy, right? So computing the joint probability distribution over a complete assignment, it's an easy thing, right? You just multiply some numbers. Yeah. Why are they redundant? There are two distinct variables. It's possible that John is on and Marie is off, and vice versa. It's actually a very, very interesting question that I will not address, but it's, if you want to think about efficient inference algorithms, you may want to think about networks that have repetitions. And maybe you want to say, you know what, these two are two distinct variables, but I'm going to model them in exactly the same way. And maybe my inference algorithm will exploit that. Yes, and that's actually true. You can imagine also thinking about, I'm going to give another example of repetitions. Let's assume that I want to look at the neighborhood, not only my alarm at home, but rather the alarm of all the people on my street. And the way I'm going to do it is I'm going to replicate this network. Now, variables are going to be distinct variables, but the modeling is going to be the same for all houses in the street. And I can come up with a smarter inference algorithm that exploits the fact that the network, the global BaseNet, consists of a lot of copies of similar things. So you're right. I mean, but these are still different variables that can take different assignments. Their modeling could be the same. So we're not going to get to it. So I'm just spending one lecture on BaseNets. If you want to know more, there is a class next semester that is devoted to graphical representations of distributions. It's an IE class, 500 level something. You can take a look. So I'm just really giving you less than a crash course on this, so can't get to everything. Yeah.
Just a question with respect to the situation that we have here. Should there be another random variable called that neighbors heard the alarm? Are we assuming that they heard it and they are getting this call?
Okay, you could invent a variable like this, but I didn't. So we can, given a story, we may model it differently. So there is a conditional probability, P of J given A, which kind of models what you said, right? It says, you know, given that John heard an alarm, or let's say, given that there was an alarm, whether John calls or not, right? You can introduce another variable that first says whether he heard the alarm, and then, given that he heard the alarm, whether he's calling or not, right? But I modeled it as one thing. But again, a story is one thing, and how you model it mathematically is another thing. Yeah?
So when you move from
Well, I'm making a lot of incorrect assumptions here too. Don't worry. But what do you mean? So you want me to model, I don't know, instead of earthquake, yes or no, some probability distribution. You want this variable to be a real valued, maybe a Gaussian, over whether there is an earthquake or not. You could do this. So you could, in BaseNet, you could have real valued variables, and then you'll have to make an additional assumption on how to model this. What's the probability distribution of this? It makes things more complicated, but it's doable. Yeah, so we're not going to deal with it. So we are going to assume discrete variables. Okay, so really my point here was to argue that you know how to compute the probability of one instance. If I give you an assignment to all variables, it's very easy. Okay, so one other definition that you will see in the literature is the notion of Markov blanket. So given a node X, the Markov blanket of X is a collection of nodes, the parents, the children, and the parents of the children. So for example, in this case, if you want to look at earthquake, the blanket of earthquake is burglary, alarm, and radio. The reason this is sometimes useful is because you can rewrite or you can rephrase the independence assumption that I phrased before also in terms of the blanket. You could say that the variable is conditionally independent of all other variables given its Markov blanket. And in some situations, this is a more convenient independence assumption to work with than the one I gave. I kind of like the first one better, but this is useful to know. So, okay, so here we have an example. So now we have a BaseNet. We already talked about the fact that, where was it? Given an instance, I can compute the probability of this instance. But typically, that's not what I want to do, right? So if you go back to the questions that you asked, you did not ask a question of what's the probability of this being 0, this being 1, this being 1, this being 0, but rather you ask what's the probability of a burglary given that I heard the alarm, or what's the probability of a burglary given that John called, and so on. So you left a lot of the variables uninstantiated, right? And that was what you cared about. So this is going to be harder to do. So let's think about what are the computational problems that we have to deal with when we represent probability distribution in general and specifically represent it this way. So first of all, we have learning problems. We want to learn the structure, right? So in this case, I invented the BaseNet. And you suggested, in fact, a different way to invent the BaseNet. You could have changed one of the arrows to go from here to there. You could have added more arrows. You could have done a lot of things. So we, in principle, given a set of variables and data, we want to be able to learn the structure. What would be the guiding principle in learning the structure? How can you learn the structure? Yeah? Okay, so that could be a good idea. So you can start with a click and then start to prune some of the edges. So this is an algorithm, what you're giving me. But what is the principle that is going to guide your algorithm? So how do you decide that this graphical structure is better than this graphical structure? What? What do you mean, the data we observe? It's maximum likelihood. That's the principle, the only one we have today, right? So basically, you want to say, okay, I have two graphical structures, and I have data. Which one of these graphical structures better explains the data? That's the only principle we have. So we will have to find algorithms to do it. And in fact, we're going to get to it in a simple case at the end of today or next time. We also have to learn the parameters, right? So let's assume you gave me a structure. You have to put the conditional probability tables on the on this graphical structure, right? What's the probability of alarm given burglary? And again, you can learn this in a supervised way. We talked about HMM in a supervised way, very easy. You look at the errors that you have, the structure is given, and you just compute statistics. You probably have to do some smoothing. If you want to do it in an unsupervised way, where you don't have, for example, the structure yet, so you learn everything together, could be a little bit harder. We're not going to talk about this. And there's the inference problem. So first of all, I want to distinguish between two inference problems. So one of them is computing the probability of an event. That is, just like what you suggested before. What is the probability of the event there was a burglary or a conditional event? What was the probability of there was a burglary given then that John called? It turns out that this is a very hard problem. And you can remember when I represented it at the beginning as a marginalization problem. Let's just go back to this. Here. We wanted to compute the probability of event. The generic way of doing it was marginalizing over all the other variables. This is a hard computation, right? If you don't care about n minus 2 variables, as we do here, you only care about 3 out of the n plus 1, it means that you have 2 to the n minus 2 things to care about and to add. Hopefully, there will be a better algorithm than this, and in this case, we show that there is a better algorithm. In general, it turns out that there is no better algorithm. So in general, it turns out that this problem is sharply complete. In fact, this was part of my PhD thesis 5 years ago. Sharply complete is the class of, hopefully everyone is familiar with NP-complete. And NP-complete, a problem is NP-complete if it's as hard as satisfiability, for example. Right? So finding an assignment, finding whether a 3CNF formula has a truth assignment. Yes or no. Sharply complete is counting how many truth assignments a 3CNF has, which seems harder, and it actually is harder than satisfiability. So it's a hard problem. This is the problem that we want to solve, right? Given two events, y and e. I'm thinking here about y and e as sets of variables, not necessarily single variables. You want to know what's the probability. What's this probability? That's going to be one key inference. Now, and this is the one we're going to talk about. There is another important inference problem in Bayes nets, or in general in probability distribution, that you will see in the literature. We're not going to talk about today. This is the most likely explanation, sometimes called maximum a posteriori assignment, MAP, sometimes also called MPE for most probable explanation. So the old literature called this MPE, the more recent literature calls this MAP. I don't know why the trend has changed, but that's the name. And really the idea is, again, as before, I'm giving you the network, and I'm giving you an observation, E. The E could be empty. Maybe I don't give you any observation. I want you to find what is the most likely assignment to variables in Y. Right? So if Y has M variables in it, there are 2 to the M possible assignments, and you have to do argmax over these possible assignments of this probability. It turns out that this problem is much easier than this problem, because you can compute the argmax without knowing how to compute all these probabilities. This problem, in fact, is only NP-complete. But these are the two key computational problems that we have to address. And we're going to talk mostly about this, and you'll see a little bit later why we care about this. It turns out that we have to solve this inference problem if we want to learn the network. Why do we have to solve it if we want to learn the network? It goes back to the explanation that you suggested, that we are looking for the most likely network, right? If we are searching for a good network, and you have two candidates, you have to choose which one is the most likely. Choosing the most likely is going to require us to compute to solve this inference problem. Okay, so we are going to start by talking about inference. There are really two approaches to inference, exact and approximate. I'm going to actually mostly wave my hands around an algorithm. There are many algorithms, some more interesting and more efficient than others. But we are going to simplify it and work on a simplified Bayes net, because it's going to make our life easier. We're going to work on tree distributions. So it's a Bayes net, but it's a tree, which means that, in fact, the independence assumption becomes simpler. X is independent of its non-descendants giving parents really means that a variable is independent of anything else giving its parent. And if you write it this way, every node has a single parent because it's a tree. Right? So simplifies the things. Also simplifies or minimizes the number of parameters. Right? So now every node is associated with these parameters, the probability of x given z. So it's a linear number of parameters now. Right? Every node, if you want, is 4 parameters or 2 independent parameters. So we have a linear number of parameters. That's good. So this is the representation that we want to deal with. Right? So this is what we need. 2 numbers for each link. P of x given z, which, as we said, is P of x being 0 given z being 1 or 0, and 1 minus them, which is P of x being 1 given the values for z. And for the root of the tree, we just need to know P of y being 0 or 1. Clear? Okay, so now let's solve the inference problem for trees. I want to know, in this case, I'm given all the conditional probability tables. I want to know what's P of x. What's the probability of the event P of x? So given the graphical structure, we should be able to compute it and what we know about probability. Essentially, what we're going to do is we're going to marginalize, let's say, P of x being 1. We can write it as P of x being 1 given z being 1. Z is the parents of x. Times P of z being 1, plus P of x being 1 given z being 0, times P of z being 0. Everything is fine. The problem is that I still don't know everything here, right? I do know P of x given z, because it's written in my conditional probability table, but I don't know P of z. But I went one step up the tree. I'm going to keep on going up. So now I'm going to compute, so recursively going up the tree, I'm going to compute P of z being 1. And again, I'm conditioning on the parent. P of z being 1 given y times P of y plus P of z being 1 given y. P of y. Now, everything is given to me. Right? I know P of z being y. It's this conditional probability table. And I know P of y because y is the root. And I'm done. So you can see that given a node, all you have to do is recursively climb up until you reach the root, and you'll be able to write the expression P of x as a function of things that you know. Yeah? Good. And maybe I should even. So I didn't say that I'm giving you the most efficient algorithm. In fact, in a couple of slides, I'm going to say that I did not give you the most efficient algorithm. My goal here is to convince you that you know how to compute this. Yes, I will cache some numbers on the way. Okay, but now hopefully I convinced you that I can do this also for z equals 0. So I can write p of x in terms of everything I know. So I can compute p of x. And it's a linear time algorithm, even without doing anything smart. Okay, let's think about another type of event, p of x and y. So So all we do is we touch the path from x to the root. And every time we have 4 numbers that we care about. Right? Because all we care about is p of x given z, p of z given y. It's Boolean, right? So it's 4 numbers. Yeah, it's exponential in 2. It's exponential in the number of values each variable can take, but I don't consider this part of my complexity parameter. Yeah. Yeah. No, everything, the only thing I need to do, the only numbers I have on the path from y to x is 4 times the length of the path. That's it. I have 4 numbers to deal with. And the sums are only sums of size 2 every time. And what's the length of this path as a function of n, which is the number of nodes? It's logarithmic, right? So I'm going to be linear. No, if x has 2 parents, I'm in trouble. But it's a tree. I'm only running this algorithm for 3. If x has two parents, then I'm in trouble. And you can see exactly why. Because then I have 2 options. Do I get to y through parent number 1? Let's assume u was a parent of x. Then I have 2 ways to get to y. I can go through z and I can go through u. And that's going to cause some problems. So I'm only talking now about trees. For trees, we're going to show that we have a very efficient inference algorithm. As I said, if it's not tree, general graphs, it's a Sharpie complete problem. Okay, so all I want to do here is I want to take a few simple events and convince you that you can compute it. So here's another simple event. Now it's joint, x and y. And again, I'm arguing that all I need to do is I need to marginalize. So let's assume I care about p of x being 1, y being 0. I'm going to marginalize by writing it as first conditional probability, p of x given y times p of y. And then recursively, I'm exploring the path from x to y. In this case, I have z, so z being 1 or 0, which I'm marginalizing over. Now, notice that here, p of x being 1 given y and z, I don't care about y. This is my independence assumption. P of x given y and z is equal to p of x given z. So it's only going to be one number here. And now, again, I've written it in terms of the conditional probability table, in terms of numbers I know. Last question is, if I have x and u, where u is not a direct parent of, or let's say x is not a descendant of u. So what I'm going to do here is I'm going to do the same thing as I did before. I'm going to try to find a joint parent. And I always have one because it's a tree. So the way I'm going to do it is, again, P of x and u is P of x given u times P of u. I'm going to climb up from x until I get to a parent, which is going to be y here. So I'm summing, marginalizing over y, P of x given u and y, P of y given u. And again, due to independence assumption, I don't care here about u. And again, I've reduced it to problems that I solved. I have to write this a little bit more, but I've shown this in the previous slide, how to write P of x given y, because x is a descendant of y. Okay, so basically, what have we shown here? I showed, quotes, in quotes, that we can evaluate the probability of all events efficiently. Hopefully, it was convincing. I didn't write formally the algorithm, but you can see that it's a simple algorithm, given that it's a tree. Right? So the question that you ask indicates that it does not show that it's going to be hard for non-trees, but it indicates that there could be a problem, and there is. And as I said at the beginning, there are more efficient algorithms. You can do a lot of caching, and you can get it to be sublinear. But really, that's what, my idea was just to show you that it's simple. In fact, this can be generalized. And I'm going to move to it in a second. But before that, it's a good time to take a break and remind you that we are getting close to the end of the semester. So the final exam is in a couple of weeks, or 3 weeks, or whatever it is, here in class, December 9. Practice or discussion or something like this of everything that we're going to cover, I'm going to do in the last lecture. Important, the last problem set, we're going to issue it tonight. It's going to be due on Wednesday. Notice that it's a weird day, not Tuesday, not Thursday, Wednesday, December 3rd. But there are no time extensions. So we moved it a little bit. So it's actually a short problem set. It's 2 problems, no programming. So you don't, hopefully, it's not going to take more than a few hours, but it's over Thanksgiving. And because you want to rest in Thanksgiving, we pushed it a little bit. But as I said again, they're not going to be, I'm not going to give the 96-hour extension. So take this into account. The reason is that I want to release the solutions just after the deadline so that you'll have the solution with you over the weekend before the final. So, yeah. It's going to be, it's going to be Wednesday midnight, Central Time. The final is in class. It's just an hour and 15 minutes, just like the midterm. Yeah. Much easier than 3 hours final, huh? Well, at least typically when I ask students, I think most students prefer a short final over a long final. So by majority, that's the... okay, and also projects. So the projects for about half of you are due on the 16th. I cannot give extensions. I already got requests for extensions. The reason is that grades are due about 2 days after. So the only way to get an extension on a project, and if you're in trouble, you may want to do it, is to get a deferred grade, which is not a disaster, That means that you have until about the middle of the next semester to do it. I don't recommend it, because you'll just get a deferred grade, whether you care or not, I don't know. But that's the only way to get an extension on a project. I just need to give the grades, I think, by the 18 or 19 or something like that. Presentations, I also got a lot of questions on that. Given that there are so many of you, I think it would be interesting to listen to 2 minutes of presentation for each project. 2 minutes is a long time if you're organized. Just because for me it would be interesting, and for you it would be interesting. I know that some of you will be out of town already, so I made it non-mandatory. If you want, we'll organize, we'll reserve a room, and we'll have a few hours of projects presentation. Yeah. I need to reserve the room, but it will not start at 8 a.m. So I think 18 is still an exam day. Okay, so if you do have an exam on the 18, send me email with the exam time, and I'll try to navigate around it. Okay, questions on the administration? Okay, so let's go back. So we talked about trees. The reason we talked about trees is because it's simple. There is a tractable algorithm. In fact, as I said, linear time algorithm. And because for trees, I'm also going to show next time how to learn. So as I said, we want to learn a representation of a probability distribution. It's difficult to learn a general representation. We will see that we can learn efficiently with a quite interesting algorithm the representation of trees. But I just want to comment, and I'm not going to go over the details, that everything I say about trees, in principle, can be said about general Bayes net, including the inference and including the learning, only that it's not going to be efficient. So there are several algorithms. One algorithm that is kind of the generic algorithm is called variable elimination. Basically, it goes like this. I'm not going to go over all the details, but we want to represent the joint, right? And we know how to represent the joint. We show this. P of joint is just the product of xi given parents. And notice that I'm abusing the notation here a little bit. It could be that the parent set is empty for some node, right? If the node is no parents, then the parent set is empty. Then this is going to reduce to P of xi. With this notation, say that I want to compute the probability of x1. This is going to require marginalizing over n minus 1 variables, which means I'm going to have a sum over 2 to the n minus 1 things, and the sum is going to look like this. Essentially, variable elimination is an efficient way of computing this, or not an efficient, a way to compute this sum so that if it so happens that you're lucky and you find a nice ordering of the variables, you sometimes get a simpler sum. That's it. I mean, in the worst case, nothing is going to happen. You will touch about 2 to the n minus 1 things, exponentially many things. If you're lucky and the network is very, very simple, or you just found the right ordering, you may get it simpler. So basically, it's a method to reorder this sum by choosing an order of variables so that it simplifies the computation. And I'm not going to go over this example now because I want to start the next thing, but I gave an example here of a very simple network and to show how this works. But really, there's nothing tricky about it. It's basically you do the sum in a given order, and it so happens that you get it simpler. Okay, so I'm going to skip this computation. It will become exponential. The worst case is exponential. In fact, the worst case is exponential even for very, very simple Bayes nets. So even if you take Bayes nets that have, I don't remember the condition now, I should remember, but very simple Bayes nets in terms of connectivity, even then, the worst case is going to be exponential. This is just an algorithm, given that you want to compute it, that, as I said, if you are lucky and you have the right ordering and there are some things that are happening in the network, it's going to be better than 2 to the n minus 1. Yeah. Average over what? So it's a, in principle, it's a good question, but it turns out that it's not so easy to define what does it mean, average, right? Because you have to decide average over what. If you want, in practice, it's hard. So if you have networks that are non-trivial, that really the complexity parameter in practice is something that is called tree width, which hand-wavingly, let's say, is how far is your network from a tree. And really, this is the complexity parameter. So if you have a network that has a small tree width, you'll be able to compute it efficiently. Otherwise, you won't. That's why in most, reasonable sized networks, people use approximate algorithms like Gibbs sampling. And I'll see how much time I have next time. Maybe I'll talk a little bit about that. Okay, I want to at least introduce what we're going to talk about next time. We want to move to the learning problem. So what is the learning problem? So first of all, I'm going to have data. Right? I'm going to have n tuples assumed to be sampled from a tree-dependent distribution. And you really have to think about whether you understand what that means. So we're going back to what we call a generative model. Right? So we assume that data is generated in the following way. First of all, you sample y according to P of y. Once you have y, you sample w according to P of w given y. And then you sample u according to P of y given, and so on. So this is how data is generated if it was generated from this tree. Right? So this is one thing to understand here. Given that, we want to find the tree representation of the distribution. And we have to think about what does that mean also. What does it mean to find that tree representation of the distribution? Yes, but in the terminology that we use in this class, it's going to be, no, I want a tree representation, not a table. I want a tree representation of this distribution. So someone gives me data. And I think, let's assume, that this data came from a tree distribution. The question is, can I even find the tree? Probably the answer is going to be no. But I want to find a tree representation of the distribution. And the only tool we have is look at all the trees and choose the most likely. Right? So among all trees, find the most likely one given the data. So basically, that's what we're going to do. We're going to compute the probability of the tree given a data, of a tree given a data, using Bayes' rule. And we're going to do argmax over this. Right? So we assume a uniform prior over all trees, and then maximize the probability of the tree given the data, which is the probability of the data given the tree. So the most likely tree is going to be this, argmax over all possible trees, probability of D given T, which is, as we said, the product over all of our example, the probability of the tree, the probability this tree assigns to this data point. Right? So we assume the data points are independent, and therefore we get this product here, and then we do argmax over T of these probabilities. Same thing that we did all the time, only that now it's a tree. And also we see why we had to solve the inference problem. So I want to just leave you with a puzzle. So, okay, so first of all, we know this, right? So we know that this argmax, because it's a tree, can be written here as pi over all variables, p of xi given their parents. Notice that we have two products here. This product is just over all data points. This product is over all variable in a given tree. And if you try this for naive Bayes, you see that what we've learned for naive Bayes was the most likely tree under the naive Bayes assumption. It's just a simple tree, right? Naive Bayes is just a simple tree where I cut this level off. Okay, so what we're going to start next time is the following thing. We're going to try a few probability distributions. And here is one probability distribution. Here is another one. Here is another one. Right? In fact, I didn't write this probability distribution because I didn't give you the numbers. But once I give you the numbers, this defines probability distribution. And given some data, we can ask the question, which one of those generated the data? But that's not going to be sufficient, right? Because this is just three possible probability distribution. The real question for us is going to be, I have infinitely many trees. Here's data. How do I choose one of these infinitely many trees? So the problem is going to be analogous to the following thing. So when we started to talk about maximum likelihood, the first question we asked was, here is a coin. It either has a bias, either it's a fair coin, or it's biased 0.6, 0.4. Toss the coin and choose which one is more likely. Two options, two hypotheses, and we chose which one is more likely. This was question one. Later on, we said, we have infinitely many possible biases for the coin. Any number between 0 and 1, choose, here is data, choose which is the right bias. Remember the difference? So we figured out a way to parameterize, we use calculus, to parameterize over p, we differentiate it and find the most likely p. We'll have to do the same thing for trees, right? Because just choosing among 2 or 3 trees is not the interesting problem. The interesting problem is, here is data, choose among all trees. So that's what we're going to do next time. Okay. So see you Thursday.
I have a couple of questions. One, you mentioned there's another 500 level course next semester.
Next semester, there is a class given by IE, Industrial Engineering.
Would you be taking?
No, I'm not teaching it.